The National Electrical Code prohibits tapping into the grounding connection between the XO terminal of a high-impedance grounding transformer and the grounding resistor for several reasons. Firstly, a neutral-to-ground potential difference is created. When a load is connected between the tap point and the lighting panel, current will flow through the grounding resistor. This causes a potential difference between the neutral conductor and ground, violating the NEC requirement that the neutral conductor be at or near ground potential. Secondly, there is a shock hazard. The potential difference between the neutral conductor and ground can create a shock hazard to personnel touching the neutral conductor or any metal parts connected to it. Thirdly, equipment damage can occur. Equipment connected between the tap point and the lighting panel may be damaged due to overvoltages caused by the potential difference between the neutral conductor and ground. Tapping into the grounding connection can lead to several dangers. 1. Injury. Shock hazards can result in serious injuries or even death. 2. Fire. Equipment damage can lead to electrical fires. 3. Code violations. The installation is in violation of code requirements, which can lead to fines and legal liabilities. The installation is not compliant with the NEC and is dangerous. To educate someone, you can firstly refer to the relevant NEC articles, for example, 250.4. A5, that prohibit tapping into the grounding connection. Secondly, explain the potential hazards of a neutral to ground potential difference. Thirdly, show examples of equipment damage or shock incidents that have occurred due to similar installations. Finally, emphasize that electrical safety is paramount and should not be compromised. Let's delve deeper into the technical aspects of high-impedance grounding and why this specific installation poses significant safety risks. High-impedance grounding systems are designed to limit ground fault current to a relatively low level, typically around 5 to 10 amps. This is achieved by inserting a resistor, in this case a 330 ohms resistor, between the neutral point of the transformer, the XO terminal, and ground. The purpose of this resistor is to limit the magnitude of fault current during a ground fault, thereby reducing the risk of arc flash and arc blast, and minimizing damage to equipment. The NEC specifies requirements for grounding systems to ensure safety and proper operation of electrical equipment. Section 250 covers grounding and bonding requirements, and it's essential to adhere to these regulations to prevent hazards. Tapping into the grounding connection, as described, directly contradicts the principles of a properly functioning high-impedance grounding system. The intention of a high-impedance grounded system is to allow only a small amount of current to flow during a ground fault. By tapping into the circuit before the grounding resistor, you are essentially creating an alternate path for current flow that bypasses the intended current limiting function of the resistor. This can have several adverse effects. Firstly, the neutral to ground potential difference is a primary concern. In a properly grounded system, the neutral conductor should be at or very near ground potential. This minimizes the risk of shock if someone comes into contact with the neutral conductor and ground simultaneously. By tapping into the grounding connection before the resistor, you are introducing a voltage drop across the resistor due to the current flowing through the lighting panel. This voltage drop creates a potential difference between the neutral conductor and ground. The magnitude of this potential difference depends on the current flowing through the lighting panel and the resistance of the grounding resistor, which in this case is 330 ohms. Even a relatively small current can create a significant voltage difference. For example, if the lighting panel draws 1 amp of current, the voltage drop across the 330 ohms resistor would be 330 volts. According to Ohm's law, voltage equals current times resistance. This means that the neutral conductor would be at 330 volts relative to ground, creating a severe shock hazard. Secondly, shock hazards are significantly increased. The potential difference between the neutral conductor and ground creates a dangerous situation for anyone who comes into contact with the neutral conductor or any metal parts connected to it. If a person touches the neutral conductor and ground simultaneously, they could receive a shock equivalent to the voltage difference between the neutral and ground. In this scenario, it could be as high as 330 volts, which is potentially lethal. This is especially concerning in a warehouse environment where workers may be in contact with metal structures or equipment that are grounded. Thirdly, equipment damage is a real possibility. The overvoltages caused by the potential difference between the neutral conductor and ground can damage equipment connected to the lighting panel. Electrical equipment is designed to operate within a specific voltage range, and exceeding this range can lead to component failure, overheating, and even fire. Metal halide high bay lighting fixtures are particularly sensitive to voltage fluctuations, and operating them outside the specified voltage range can shorten their lifespan and increase the risk of failure. Furthermore, the improper grounding configuration can interfere with the proper operation of protective devices such as circuit breakers and fuses. These devices are designed to interrupt the flow of current during an overcurrent or short circuit condition to protect equipment and prevent electrical fires. However, if the grounding system is not properly configured, these devices may not function as intended, increasing the risk of damage and fire. Code violations are also a major concern. The NEC provides detailed requirements for grounding and bonding to ensure the safety of electrical systems. Tapping into the grounding connection in the manner described violates these requirements and creates a non-compliant installation. This can lead to fines, legal liabilities, and potential insurance issues. Electrical inspectors are responsible for enforcing the NEC and ensuring that electrical installations meet safety standards. If an inspector discovers a non-compliant installation, they may require it to be corrected, which can be costly and time-consuming. There is also the risk of electrical fires. Equipment damage caused by overvoltages and improper grounding can lead to electrical fires. Overheated components, damaged insulation, and arcing faults can all ignite combustible materials in the vicinity, leading to a fire that can quickly spread and cause significant damage. Electrical fires are particularly dangerous because they can be difficult to extinguish and can release toxic fumes. In summary, the installation is dangerous and violates the NEC because it creates a neutral to ground potential difference, increases the risk of shock hazards, can damage equipment, and can lead to electrical fires. It's essential to correct this installation to ensure the safety of personnel and protect equipment from damage. To effectively educate someone on this matter, it's crucial to provide clear and concise explanations of the technical principles involved and to emphasize the potential safety hazards. Start by explaining the purpose of high impedance grounding and how it limits ground fault current. Then explain how tapping into the grounding connection bypasses the intended current limiting function of the resistor and creates a neutral to ground potential difference. Use Ohm's law to illustrate how even a small current can create a significant voltage difference. Emphasize the potential shock hazards associated with this voltage difference and explain how it can lead to serious injury or death. Provide examples of equipment damage and electrical fires that have occurred due to similar installations. Refer to the relevant NEC articles that prohibit tapping into the grounding connection, such as 250.4. A5. Explain the code requirements for grounding and bonding and how the installation violates these requirements. Show diagrams and illustrations to help visualize the concepts and make them easier to understand. Be patient and willing to answer questions and address concerns. Some people may be resistant to change or may not fully understand the technical aspects of the situation. It's important to remain calm and professional and to provide clear and accurate information. Emphasize the importance of electrical safety and the need to comply with the NEC. Electrical safety is not something to be taken lightly, and it's essential to prioritize safety over convenience or cost. Remind them that the purpose of the NEC is to protect people and property from electrical hazards, and that it's in everyone's best interest to comply with these regulations. If necessary, consult with a qualified electrical engineer or inspector to provide additional expertise and support. A professional opinion can help to reinforce the importance of correcting the installation and to ensure that it's done safely and properly. In addition to the points already discussed, it's worth noting that the impedance of the grounding resistor is carefully selected to achieve a balance between limiting ground fault current and allowing sufficient current to flow to activate protective devices. The 330 ohms resistor in this case is likely chosen based on the specific characteristics of the electrical system and the available fault current. Tapping into the grounding connection changes the overall impedance of the grounding system and can disrupt this balance. This can have unintended consequences, such as reducing the effectiveness of protective devices or increasing the risk of transient overvoltages. Transient overvoltages are brief spikes in voltage that could occur due to switching operations, lightning strikes, or other disturbances. These overvoltages can damage sensitive electronic equipment and can also pose a safety hazard. A properly designed grounding system can help to mitigate the effects of transient overvoltages by providing a low impedance path to ground. However, if the grounding system is not properly configured, it may not be able to effectively suppress these overvoltages. Furthermore, the connection to building steel is only effective if the steel has been designed and constructed in such a way that it can be used as part of the grounding electrode system. There are specific provisions in the NEC regarding using building steel as a grounding electrode, and these provisions must be followed to ensure that the steel is properly bonded and connected to the electrical system. It is not appropriate to arbitrarily connect a grounding conductor to building steel without verifying that it meets the requirements of the NEC. In conclusion, tapping into the grounding connection between the XO terminal of a high-impedance grounding transformer and the grounding resistor is a dangerous and non-compliant practice that should be avoided. It creates a neutral to ground potential difference, increases the risk of shock hazards, can damage equipment, and can lead to electrical fires. It's essential to correct this installation to ensure the safety of personnel and protect equipment from damage. Remember, electrical safety is paramount, and it's always best to err on the side of caution. Consult with a qualified electrical professional if you have any doubts or concerns about the safety of an electrical installation. Let's also talk about the type of lighting being used: metal halide high bays. Metal halide lamps are known for their high efficiency and long lifespan, but they also have some characteristics that make them more susceptible to damage from voltage fluctuations and grounding problems. Metal halide lamps contain a mixture of mercury and metal halides, which produce light when an electric arc has passed through them. These lamps operate at high temperatures and pressures, and they are sensitive to changes in voltage and current. Voltage fluctuations can cause the arc to become unstable, which can lead to flickering, reduced light output, and premature lamp failure. Grounding problems can also cause problems with metal halide lamps. If the grounding system is not properly configured, it can create circulating currents that can damage the lamp ballast and other components. In addition, metal halide lamps can generate electromagnetic interference, which can interfere with other electronic equipment. A properly designed grounding system can help to minimize electromagnetic interference and ensure the proper operation of metal halide lamps. Furthermore, when dealing with high bay lighting in a warehouse setting, compliance with relevant safety standards is important. OSHA has rules on the use and maintenance of electrical equipment in workplaces to protect employees from electrical hazards. These regulations cover things such as wiring methods, overcurrent protection, grounding, and the safe use of electrical equipment. Employers are required to ensure that electrical equipment is properly installed, maintained, and used in accordance with these regulations. In addition to OSHA regulations, the NEC also contains specific requirements for lighting in commercial and industrial buildings. These requirements cover things such as the type of lighting fixtures allowed, the spacing of lighting fixtures, and the control of lighting. It is essential to comply with these regulations to ensure that the lighting system is safe and energy efficient. The situation underscores the need for continuous training and education in the electrical field. Electrical codes and standards are constantly evolving, and it is important for electricians and other electrical professionals to stay up to date on the latest changes. Training programs, seminars, and online resources can help to provide the necessary knowledge and skills to ensure that electrical installations are safe and compliant. Furthermore, it is important to foster a culture of safety in the workplace. This means encouraging workers to report potential hazards, providing them with the necessary safety equipment, and ensuring that they are properly trained in safe work practices. A strong safety culture can help to prevent accidents and injuries and to create a safer working environment for everyone. In summary, dealing with electrical systems requires a thorough understanding of the relevant codes, standards, and safety practices. By adhering to these guidelines and fostering a culture of safety, we can help to prevent electrical hazards and ensure the safety of people and property. Also, I will add in that in an industrial environment, the presence of harmonics should be accounted for. Harmonics are distortions to the pure sine wave nature of alternating current and voltage, and they can cause a variety of problems in electrical systems. Nonlinear loads, such as variable frequency drives, electronic ballasts, and computer power supplies, are major sources of harmonics. Harmonics can cause overheating of transformers and conductors, nuisance tripping of circuit breakers, and malfunction of electronic equipment. In a high-impedance grounded system, harmonics can exacerbate the problem of neutral to ground voltage. Harmonics can create additional circulating currents that flow through the grounding resistor, increasing the voltage drop across the resistor and raising the neutral to ground potential. This can increase the risk of shock hazards and equipment damage. To mitigate the effects of harmonics, it is important to use harmonic filtering equipment. Harmonic filters are designed to reduce the level of harmonics in the electrical system and to prevent them from causing problems. There are different types of harmonic filters available, and the appropriate type of filter will depend on the specific characteristics of the electrical system and the types of nonlinear loads present. Another factor to consider is the type of cable used for the grounding conductor. The grounding conductor should be sized appropriately to carry the expected ground fault current and should be installed in accordance with the NEC. The NEC specifies the minimum size of grounding conductors based on the size of the overcurrent protection device protecting the circuit. In addition, the grounding conductor should be made of copper or other corrosion-resistant material to ensure a reliable connection to ground. It is also important to ensure that the grounding conductor is properly terminated at both ends. The termination should be clean, tight, and corrosion-resistant to ensure a good electrical connection. Loose or corroded connections can increase the resistance of the grounding path and reduce its effectiveness. Finally, it is important to regularly inspect and test the grounding system to ensure that it is functioning properly. Ground resistance testing can be used to measure the resistance of the grounding path and to verify that it is within acceptable limits. Visual inspections can be used to identify any loose or corroded connections or other problems with the grounding system.